That's starting the application process. Yeah, except I think it counts as why the policy is I feel so good about myself. Just think I need to so like I think what's most is like the lowest are yeah,
Hello, good morning. Regarding the grading for midterm 2, it's still going on. I'm the one who is grading. I expect it to be done today. I was hoping the weekend I'll be able to finish it. I've done it halfway and that should be completed today. Homework 4 is due Wednesday. And midterm 2. Any general questions? We try to be good with the camera today. We have been working on the idea of electric energy. Electric force is given by the Coulomb's law. Two charges, anytime we have a positive and a negative charge, they attract. Positive and a positive charge, they repel. So those are forces, those are electric forces. And whenever we have electric force, we can think of an energy. How do you store energy? For example, you would like to go against the tendency of the charge, like a positive charge, the electric energy, let's say, or energy in general. Electric energy, a positive charge and a negative charge tend to come together. And if you were to exert or find a mechanism that will keep it apart, that means there is a stored energy in it. In what sense is it stored? That if you were to remove that mechanism which keeps it apart, it will go towards each other and in that process release the energy. Right? That's a simple idea of a battery that we have, that we use for all our devices. Basically, that's electric energy. You keep the charges separate. You will see that on a battery, you have positive and a negative. That means you're using chemical properties or mechanical properties. You keep them separate. And the moment you release them, they come together. And in that process, release the energy, which we use it for other purposes. Usually, these days, we use electronic devices so much, we use it to run that. So we would like to make these definitions precise. We already talked about electric energy for a point charge, electric potential, and electric energy. We want to make it, we have been talking about two configurations. One is parallel plates and one is point charges. Today we want to talk about parallel plates. Let's have the same charges this time in a configuration where you have two plates. This is experimentally much easier to attain. You just take two metallic plates and keep it together. And let's have negative charges on the top plate. Again, remember, how do you very naively create charge? You just rub it, right? Any surface, when you rub it against something else, you have a charge on it, and there is a good chance that you will have negative or positive charge on it. But with a little bit of expertise, you can make sure how much charge is being collected on a surface. So that's a positive charged plate, and let's say these are there is negative charge Q here, and there is positive charge Q. Often, when the plates are very large, we talk in terms of charge per unit area instead of charge itself. So often we say this is charge per unit area. And that's simply Q over A. How much charge that is on the plate divided by the area of the plate. What is the electric force a charge would experience? That's given in terms of electric field, and these are the electric field lines. For a parallel plate configuration. At the corner of the plates, they tend to bend a little, but we are pretending that they are extremely large in size so that we don't have to really worry about this corner. The edge effects are not really there. Pretend that they are going all the way to infinity. In that case, the electric field for this we have studied is equal to, let's talk in terms of magnitude. That is a direction which is in the upward direction. The magnitude of this electric field has this very simple expression in terms of charge per unit area, and it's simply sigma over epsilon naught. Oh, epsilon. If you want to write it in terms of Q over A, that's equal to Q over epsilon naught times A. Just to substitute that in. And that's the electric field. Whenever you see parallel plate configuration in your model that you are trying to investigate, or in our case in homework problems or in exams, whenever you see a parallel plate configuration, you want to think of electric field being a uniform electric field. Everything is the same. Even however close you get to the plate, it's exactly the same. What is the energy stored in it? Energy is equivalent to electric potential. Remember, potential is energy per unit charge, and that's given by if you were somewhere here, this is at a higher potential over somewhere here. And whenever we say this, we are talking in terms of positive charge. So this is higher potential. And this is lower potential. And these lines are called equipotential surfaces, in the sense that if you were to move from this point to this point, it does not cost you energy because the force is perpendicular to that. You don't have to spend any energy to go from this to this. It's like gravitational force. If you're going horizontally, you don't spend any gravitational energy. It's only when you go vertically up there is a gravitational energy spent. You might be spending a lot of energy, your muscles might be spending a lot of energy, but that's not what we are saying. What is the work done by the gravitational force. In this case, what's the work done by the electric force? And that is equal to 0 whenever you're going perpendicular to the direction of the force. And in general, what's the potential difference between them? That's equal to, so potential difference, electric potential difference is given by, so we say it is change in potential. That's whenever I say delta, it means that it's a V final minus V initial or V2 minus V1. In this case, for an intuitive feel for what we are talking about, it is the potential difference between the two ends of your battery, or if you think of a wall socket, it is the electric potential difference between the two points in that wall socket. Yes. And that's given by, it is force times distance. So how far do you take this charge? You take this charge from here and you lift it and put it there. So it's traveling a certain distance d. So that's your d here. And it is electric field times the distance d. How do we motivate that? Remember, this is potential energy is, electric potential is potential energy times charge q, whichever charge you're moving, and potential energy itself is force times distance. So that's q times the electric field. That's a force experienced by a charge in an electric field, and times distance, force times distance. Let me say this is force, and divided by q itself. Q cancels out. So that's E times G. So instead of talking in terms of force per unit charge, this is energy per unit charge. How much energy is needed to move a unit charge from a certain point 1 to certain point 2. So that's the expression you want to keep in mind. But we know that electric field for a parallel plate capacitor has the simple expression, simple in the sense that it does not depend on any parameter significantly. It is just charge, how much charge you store times A. It does not depend on the distance, how far it's uniform electric field everywhere. So how much is the potential difference between these two plates? That's your how much energy is stored in your, or can be stored in your battery, like a cell. And that's what we are going to calculate here. So this is sigma over epsilon naught times d. Let's talk in terms of charge. So this is charge and epsilon A and d over A. That's how much energy per unit charge. This is not energy, remember, this is energy per unit charge. Let me clarify. This is energy stored per unit charge. Like energy overcharge is how much energy you stored by if you were to move a certain amount of charge from one plate to the other. You would like to know the total charge also. That is what you have in your battery. This is per unit charge. This is in the sense potential, right? How much can it store? We'll come to that in a few minutes, but let's define a quantity here while we are having the electric potential in hand. And it's a good quantity to define that this is Q over C. So whenever you have a parallel plate, we can define a quantity called C, which has to be read out from here. This will be called the capacitance. It is a measure of how much energy can be stored inside a capacitor. So often we will stop writing this delta V whenever it's like saying time. If we are measuring delta T, if you set one of the times to be 0, then we just have to talk about T, not delta T. Similarly, a standard equation you will see is V is equal to Q over C. So that's voltage or potential difference. Often we say voltage. This is charge. And that's capacitance. All three are interrelated and connected. If you know the voltage or the potential difference, you know how much energy can be stored in there. If you know charge, you know how much energy can be stored in there. And if you know the capacitance, that's also a measure of how much energy can be stored in there. Capacitance is nice in the sense that it is dependent only on the geometry of the device that you're making, or for example, the battery, or in this case, the capacitor itself. See here, if I were to read this out for a parallel capacitor is equal, it's in the denominator, so I have to invert everything. So that's equal to epsilon naught times area divided by the distance d. So if I want to know how much is the capacitance of this capacitor, so you would say capacitance of a capacitor it is a geometry dependent quantity in the sense, how do you design your capacitor? In this case, this was straightforward. We took two parallel plates and built this, but often when you're building electronic devices, it's not convenient to make parallel plates. It takes a lot of space, for example. So often you roll it. So you take these two plates and you have charges on it, but you will roll it into a cylinder. So you would do this kind of a configuration, and you have another plate in here, and there is a material in between so that they don't touch each other. That is one very simplistic way or a practical way of doing it. But when you try to calculate the capacitance for this, it is slightly more work. If you want to say mathematically, it's slightly harder, but most of the qualitative features is captured when you just imagine that it is a parallel plate. So capacitance of a capacitor, in our case, we are talking about parallel plate capacitor. Is given by C is equal to epsilon naught times A over D. Notice there is only physical parameters coming in, right? Area A and how far are these two plates. That's the only thing that decides how much is the capacitance of a capacitor. This is an electric property of vacuum. So that's all that depends on. Let's very quickly see what exactly is the capacitance of a very simplistic capacitor that you can build. So let's say you try to build a capacitor using this following configuration. You take this is an aluminum foil. Just spelling up a minute. It's different in British English and American English, so I get confused. I think it's aluminum, right? I guess, yeah. Aluminum, the foil that we use in kitchen. Hopefully that's clear. And let's take two of them. And place it like this, one over the other, and they touch each other, and you don't want to keep it touching, so you keep a thin